Okay, this is the lab for the differentiator. So what I'll do is just go over some of the components that make up the circuit. Um, so first of all, here we've got a generator. It's an audio generator. It's going to be putting out 10,000 hertz as a sine wave out. Well, actually, we're going to start off with a square wave. I'll do the sine wave after the square wave. So we're going to keep this circuit unchanged for the sine wave and the square wave. Although later I'm going to swap over these components so I can show you the difference between the voltage across the capacitor and the voltage produced by the audio generator, so you can see the difference. But I'll do that at the end. So we're going to have a capacitor there, the resistor. I'm going to change resistors. This is going to be a resistor box. So here we're showing the drop of voltage across the resistor box. So this is the voltage. I'm not showing the ground leads here to the oscilloscope channels, but obviously they've all got a ground lead. So here I'm taking the voltage across the capacitor and the resistor, because remember that both the voltage across the capacitor and the voltage across the resistor is basically V in. So when I'm looking at channel 1 here, I'm looking at V in effectively, and here I'm looking at the V out, which is the voltage dropped across the resistor. So when we run this circuit through, we'll get a square wave at the top on this. This will be the voltage across all of this. So that's obviously that's your voltage input. So we're going to see a square wave. So that's exactly from the audio generator. And then what we'll see across the V out is this pattern. Now the reason, going back to the tutorial, just to revise the tutorial a little bit here, the reason we're seeing this pattern here is, if we look at this little box here, it kind of describes it. When the capacitor is charging, we get this typical RC charge curve here. So at the square wave here, the capacitor itself is doing this, and we're not showing the capacitor voltage, but we know that the voltage dropped across the resistor is for example, at the beginning here, there's no voltage drop across the capacitor. So if we imagine we just switch this on, at the very first instance there's no voltage across the capacitor. So obviously the current then is flowing at its fastest rate. So because it's flowing at its fastest rate, and we effectively got no charges accumulated on the capacitor, that is basically a short circuit. So all of your voltage at that moment in time is going to be dropped across this resistor. So hence you get this sharp peak in this little box here. So across the resistor, at the very first instant, when there's effectively a short, you get a spike. And then of course, as you see, over time the capacitor starts to charge up. So we get less and less voltage dropped across the resistor, and more voltage dropped across the capacitor, until we reach the capacitor when it's fully charged. All of the voltage virtually is dropped across the capacitor, and then we get to the point where there's nothing dropped across the resistor. So that's why you're getting these spikes. And it's the same when you go from up here, the capacitor is fully charged at this point, and then it drops down to 0 again. Well, you get a spike in the opposite direction then, because obviously the charge is the capacitor is discharging then, and then the voltage at that point, then you're getting a negative voltage coming back out, and so obviously you get this minus as the voltage is coming back out, back into V in. You're going to get this minus spike here, so hence you get the minus spikes. So that's really why you're getting these this correspondence between V out and V in. And what it's effectively doing is it's showing you this gradient here, which is why we call it a differentiator, because it's showing this gradient. So I'm just going to show you physically how that's working, and let's just have a look at the circuit first. So very simple circuit again. It's just our RC circuit. So nothing special going on. It's probably not going to be easy to see these components, but obviously there's only one component here that you can see in the breadboard, which is the 220 picofarad capacitor. Now here's the decade box here. This decade box you've probably seen a few times now. That can range from 0 ohms up to 10 megs, so we've got plenty of range there to test things out. And connected to the input, so obviously we've got V in, which is just a very basic audio generator. So here you can see that's been set at 10 kilohertz, and to measure both the voltage across the total voltage V in, to measure so we can see that what's happening there on that audio, and the voltage across the resistor. We're just going to use an oscilloscope. So basically that's the setup. So I'll leave it pointed at the oscilloscope because that's probably the most relevant thing we're going to see here. If I just straighten that up a little bit. So if we look at the scope now, and what I'm going to do is just switch this on, or I just turn up the brightness and see where we are at the moment. So at the moment, I don't know how well that's going to come out, but along the bottom here we see those exact spikes. Now I can reduce this down, I can zoom in and look at this a bit closer. So here you can see the spikes here. So for example, we're going from low to high in this square wave. We get this, the voltage across the resistor is peaked up here. Exactly the same thing. Now we can see the discharge, we can see the charging up of the capacitor simply by seeing how the voltage drops across the resistor. So you're going to get that, you're going to be able to see that familiar discharge, what looks like a discharge of the capacitor. And basically it's the capacitor charging up, and obviously the voltage then is all dropping across the capacitor. So we can see that by increasing the resistance, because obviously if we increase the resistance we're going to slow the current down. So the more we increase the resistance, the slower the current becomes. Therefore then the charge, we're going to be able to see this charging of the capacitor more clearly, and also we'll see that how, here we go, I'm going up now, so I'm up to 5,000 now, and as you can see now, you can clearly see I've gone back to 0. So if we go up to say 10,000, or yeah, let's go to 10,000. Now we go to 11,000. Now you can see quite clearly what's going on here. So the capacitor, I'm showing the voltage across the resistor, but because the capacitor is charging, as I showed in my diagram before, that's going in this direction. Remember, this is V in, not the capacitor voltage. But the capacitor itself is doing this, in exact opposite to that. So obviously, as more of the voltage is dropping across the capacitor, less dropping across the resistor. So that's why you get this differentiator effect. We call it differentiator because basically it's the gradient of this. If obviously we bring the resistance right down, let's bring that right down. The lower we make this, let's bring it right down. So you can see the lower we make the resistance, the faster the charge is going to go up. So this charging rate is going to be much quicker. So then we get a much closer representation of the, I don't know if you can see that. We'll get a much closer representation of a differentiator. So that's the square wave. Next we're going to look at the sine wave, which is pretty much the same. All I'm going to do here is I'll just go back to where we are here. So all I'm going to do with the sine wave is just on the audio generator, just switch it over. I'm actually currently fixed on it as a square wave. So all I'm going to do with the audio generator is pull that over to a sine wave, and then we'll quickly just talk about this for a sec. So here I've just drawn down what we're going to see here. So similarly here now, in this case, it's not a square wave anymore, but just looking at one part of the sine wave curve here, this part round here, I've also, over the top, I've drawn in the typical way the voltage across the capacitor will be charging up. Although you won't see that on the scope, but I'm just drawing it here to give you an idea. And here you can see initially the capacitor is 0 and it comes out of the gate quite fast, but because it's 0, obviously that means all the voltage is dropped across the resistor. So again, we get the maximum value here, which is also shown here. So for example, if we're just coming out of the gate here, now the capacitor at this point is empty. It's beginning to charge up here. Because it's empty, all the voltage gets dropped across the resistor here. Now remember, this is also a proxy for the current, because obviously the voltage that drops across the resistor is exactly proportional to the current, and because we're using a really small resistor, this becomes even closer representation of the current here. So this V out here can also be thought of the behavior of how the current is. Yeah. So here, as I say in this diagram, as we start to come over and we're fully charged at this point, obviously once we're fully charged, then the voltage on the output then is 0, because we're fully charged at that point. And then of course as it's a sine wave, it'll come back through here and we'll go on. We'll be able to see all that. As we discussed in the tutorial, the pattern that we make here is like a 90-degree shift or a pi/2 degree shift, so that this voltage out, which again is the proxy of the current, is leading the voltage in by pi/2. So let's have a quick look at that now. I'm gonna just adjust the right. So if we look at the scope now, I've got that set up on the scope. If I can get this round. Okay. Right, on the scope here we have, just bring this down so we can see what's going on. Right, the top curve, this top one, this is the voltage input. So at the bottom curve is the voltage across the resistor, which you can think of as the current as well, if you like. So this is the crossover point. This is I'm taking this as the 0 point here. So in fact I shall just move that down a little bit just to give it a, so it's right in the middle of that, of this actual central graticles here. I'll just line it up there. So now we're coming across the central part of that. Just get that down there. Okay, so now you can see if I move this one up at the fastest when the voltage is changing it at its fastest rate, that's when you're going to get, obviously at that point, the capacitor there, as it crosses through the center, is completely discharged. So then you're going to get maximum voltage drop across the resistor, and there you go, you can see it, there's the maximum. So I've got the scope fixed up across the resistor on one channel and the scope fixed up on the total V in, which is the voltage cross cap plus the voltage cross the resistor, which is this initial curve. And here we can see it. So we've got, and if you look at that, that is pi, that is 90 degrees shifted. So this one that I'm moving up and down leads the voltage by pi/2. It leads it by 90 degrees. So you can think of the voltage in as a sine wave. You could think of the voltage out as a cosine. And if you've done any calculus, you know that when you differentiate a sine, you get a cosine. So so there you go. You have got a differentiator there, and the reason it works is because of the way that the capacitor is charging and the voltage is dropping across the capacitor. Any voltage that drops across the capacitor is not dropping across the resistor, and vice versa. So that is what is actually. So although it might sound, when you hear the word differentiator, might sound very complicated, that's in essence all it is. It's a sharing of voltage between the resistor and the capacitor, And if you understand how the capacitor works, in other words, it's two empty plates initially with no charges across the plates, and then over time the charges accumulate till eventually the capacitor has so many charges on it that the charges add up to a voltage which equals the input voltage. And I'm not showing the capacitor, I'm just showing the input voltage. But at that point, both the capacitor voltage and the input voltage are the same, and that will equate to, here, this will be the crossover point here across the zero, and that will be when there's no voltage across the resistor. So that point there is no voltage across the resistor. So that's that. The next thing I'm going to do is I'm going to swap over the components and just show you what I've got here. What I'm going to do now is just going to quickly read this now. So on the breadboard, what we're going to do, I'm going to swap over the resistor box and the capacitor. I'm going to just swap them out. I'm not going to change anything at all on the circuit. I'm simply going to swap those two components over so that I can show you the difference between the voltage in, and this time we're going to be able to see the capacitor voltage and the difference between the capacitor voltage and the difference between the voltage in. So that's what we're going to see. So in the diagram, during the tutorial, I went through a whole thing about explaining how the voltage across the capacitor was slightly delayed. So there's a slight delay there between the V in and the VC. The VC comes later because obviously the whole thing is driven by the voltage in, so it takes some time to charge the capacitor up. Now I've swapped these over, I've dropped the channel 2 across the capacitor, and channel 1 now represents again the whole of the voltage input, but now we're going to be able to see the voltage in versus the voltage across the capacitor, and we'll see this delay. So we won't see the delay though if we've chosen a very small resistor and a very, well, this is fixed at the moment, so that's 220 picofarads, but if we have a very small resistor, as in 0 to begin with, so if we set that to 0 to begin with and then look at the scope, we'll see that what looks like one curve, because there's no delay in effect. So if we look at that now, here we see there's one curve. I'm going to bring the brightness down a little bit here. I don't think it's needed all that bright, seems to be picking it up quite well. And to see the difference, you need to bring the brightness down a little bit, I think. So okay, I'm going to now start to increase the resistance. So now what we're going to do when we're increasing the resistance, I'm going to start switching up the decade box, and by doing that I'm slowing down the charges that are accumulating on the capacitor. When I slow down the charges that are accumulating on the capacitor, that means I'm going to increase the delay, because it's going to take longer to charge the cap up. Therefore, when we look at this curve, we'll eventually see two curves. So let's just move it up, and I don't know if you can see that there it's moving. So we're up to 8,000. Now you should be able to see two curves now, but if I go to an extreme and take it up to 10,000 ohms, we should see quite a marked difference. There you go, you can see. So we've got a delay there. If I move the one that's delaying, that's the delay. So that's the voltage across the capacitor, and you can see it's delayed. There's a slight gap there, and it comes after the voltage in. So there you go, that's proved. So if you did believe it in the tutorial, there it is. The voltage across the capacitor takes time. It takes a little bit of time to catch up with the voltage in, and that's what's going on. And that's why you get this the carriers, the charges going between voltage in and voltage and the capacitor. So you know, during this upswing here, right? So if this part here, you can see that the capacitor voltage here is above in value the input voltage. Now, because the capacitor voltage is slightly higher in this part of the curve here than the voltage in, then obviously charges are going to go from the capacitor back into the V in, because obviously the sine curve now is going in the opposite direction. It's negative, yeah. And then on the other side, you can see from here to here, now the capacitor voltage, you can see now the capacitor voltage here is lower. Can you see that? It's lower now than the input voltage. So because it's at a lower voltage than the input voltage, the charges are going to flow from the input, the voltage into the capacitor. So now they're going, if you like, in a positive direction. They're going from the voltage in, and they're depositing on the capacitor. And then again, if you just carry on saying what we're saying here now, this part down to here, they've swapped again, yeah. So that's what's going on. So what I did then was I actually started to measure this gap so that you could see the difference, and I just quickly discuss what I've done there. Okay, so I just read this. So what I've just written here, approximately every 1,000 ohms, the resistance is increased for a frequency of 10 kilohertz. We get and this is only applies to this particular setup. This will be different for different frequencies and different for different combinations of resistors and capacitors. So I'm not saying this is any given proportional relationship here. But for this particular case, we get an increased delay time by 0.5 microseconds. So it seems to jump up each time by 0.5 microseconds. With R equals 0, we are unable to measure the delay as it is too small to register on the scope. So when there's no resistance, we actually see both the curves superimposed on top of one another, as I originally showed you. We can clearly see that each increase in resistance causes a proportionally longer time delay. So as we went down, the two curves are almost superimposed with a very small time delay. And obviously this really, all I'm doing here is just showing that when you increase the resistance, you get a longer time delay. And the oscilloscope, I showed you that on the scope, as I increased the resistance, that gap between the two of them got bigger and bigger. So that's that. That's this lab over. In the coming lectures, we're going to start talking about phase differences and how to calculate phases with different signals, and that gets a bit more interesting. It's also can be a little bit more difficult to understand, but not any more difficult than what we've just gone over in this last tutorial. So I think you'll find it more interesting than difficult. Okay, thank you.